Okay. All right. Let's. Can you see my slide?
Yes.
Yeah. Okay. Great. All right. Welcome everybody. So this is the final day of our Cloud Edge training. Right. I think we have one more session tomorrow, but it's going to be led by some other folks. And next week, we'll Mihail and I will work with the fellows, and guide them through their capstone project. So, think of today as basically the payoff for whatever we have done until today, right? So Tuesday we basically built a cloud system that has basin level intelligence, right? And on Wednesday we built a single device, that sits in a creek somewhere upstream, right? And today, and both of these two things have their own blind spots. And today, we will not build anything new, but think about how to combine these two things together, right? So that we can build a better early warning system, which is mostly how every serious system it probably works, right? So this afternoon, the session Mihail is going to lead, you'll assemble a full pipeline, right? Will basically the thing that we did yesterday, a single sensor will create copies of it and mimic a fleet of smart gauzes, right? And then the cloud that you and each of these gauzes will send signals to the cloud system that we built on Tuesday, right? And we'll send messages both ways, usually data going up and instruction and intelligence coming down. And uh, and and we'll see how this system is going to be better than any of these two independent systems, right? Either just the edge devices or the cloud devices. Okay. Right. So this is what we have done so far, right? On Tuesday, right, was the cloud half, right? And the what we saw was these big data systems, they are already in the cloud, right? And we pulled USGS data, right, for one stream flow, which is just one API call away, right? And then we built a stream flow nowcast, right? So basically, we did a 1 hour ahead prediction, right? And then we scored with NSA, and we kind of saw how to do this elastic scale up and scale out, right? So how do you move up and move down? So the weaknesses of and we also discussed shortcomings of the cloud computing, and one of the key bottleneck was that so if the data is coming from real-time gauzes, then the underlying assumption is the network is always operational, right? And for the catastrophic events like floods and storms, this assumption goes out the window, right? So this may not always work. On Wednesday, right, on the other hand, we built a river gauze, right? So basically, we thought about the system that interacts with the river itself, right? And how do we push intelligence towards that device, right? How do we do computing at the edge of the physical and digital world? So we built a smart gauze, right? So and we saw like a dumb gauze that just collects the data, right? We also saw that, and then we also built some slightly smarter gauze which has an adaptive rule, right? And so which has rules for threshold and sending out alerts, and also does adaptive sampling, right? And we saw that there was a clear advantage, right? You could get away with sending like 25 messages a day instead of 1440, right? And we also discussed that these radio transmissions are what consume most of the power of a edge device. So this was a significant advantage, right? And we saw how a smart gauze, right, can warn the system, right, warn the town nearby, right, through SOS and secondary communication channels, even when the network is down, right, even when the primary communication channel is down, right? So there was some clear advantage there, right? But we also know that because a edge device is at a particular location, it only knows the data from that particular location, right? It doesn't see what's going on upstream, it doesn't see what's going on downstream, right? It cannot, it doesn't have the full picture. right? So, but if we think about it, right, so these two paradigms, right, competing paradigms, right, either like push the collect centralized collection of data and centralized computation, or this distributed computation, at the point where the data is itself collected, they have complementary weaknesses, right? And one fails exactly where the other is strong, right? So so that basically tells us that we can do something smart by combining them, right? And we can get the best out of both of these world. Okay, so let me remind you, right, that Mihail and I are, we are monitoring the chats, we are monitoring the Q and A's. So please feel free to send questions our way. Hopefully, you had some chance to play around with the system that we have built on Jetstream, and if you have some insights, if you have something more interesting to share, please keep sending them our way. Okay, all right, let's move on. Right, so what are we going to do in the next 2 hours? Right, so first we'll talk about we'll expand on what we already know. Right, so because on Tuesday we went over the entire cloud systems. Right, we talked about when cloud is powerful, what is the advantages and so on. But we also discussed their limitations. Right, and we did exactly the same yesterday when we talked about edge computing, right? We talked about where it's most powerful, where it can help the most, right? And where it also fails, right? So we'll recap that, right? And then we'll also think about how this cloud edge complementary advantages allows us to address them, right? And this leads us to module 2. Well, we'll talk about how to get the best out of the advantages of cloud and edge, right? So basically, how do we combine them, right? And 5 standard ways, right? That are out there that people use to build the hybrid systems, right? And then in module 3, we'll apply the patterns of our flood system, right? Computation by computation, right? So we'll basically uh, design our pipeline, right? We'll think about how an architecture could work that is and where the computation should be, right? At which level the computation should be. Then we'll talk about the communication channels, right, between the cloud and edge devices. So at this point, the edge is not a single edge device, and a cloud is not that meaningful, right? So there are multiple edge devices that are spread through the world, river system, right? And those have to talk to the centralized cloud computing, right? So we'll talk about MQTT, which is the protocol that the is the IoT devices use to talk to each other and talk to a centralized system, right? We'll think about message design, fusion, and we'll close the loop. Then we'll talk about, we'll give some examples, right? Like a similar to what we did on Tuesday and Wednesday, right? We'll talk about how the real systems are built, right? So the systems that you're familiar with, right? We'll talk about NWM, right? National Water Model, and IFIS, right? So I'm sure you guys have used IFIS and NWM data in your research so far. So we'll think about how hybrid computation enables these systems, right? And then we'll do preview of we are going to do this afternoon, right? And the actual system will be led by Mihail this afternoon. Okay, any questions so far? Okay, if not, let's move on. Okay, so this is this is the slide that we have been bringing up every day, right? On Tuesday, we pulled the river data, trained a forecast model on a rented supercomputer, right? There was a big centralized machine. We kind of assume that that machine has access to the data, right? And then we rented a small chunk slice of that computer to basically do our necessary computation. On Wednesday, we did the exact opposite, right? We pushed the intelligence out to the sensors, right, on the real world, right? Instead of thinking about the most central system, we went out to the boundary, right? And we did now, because the edge devices have limited computing resources, right? We couldn't do much. right? Even in our simulated system, we could only have implement some small logic, right? So which sends out checks whether the water level is above a certain threshold, or the rate of rise is above the certain threshold, and also sends out messages, right? And we also saw how this uh, how to do adaptive sampling there, right? So you don't want to keep sampling data every few minutes when things are relatively stable, right? So you kind of want to your rate of sampling can go up or down depending on a real threat of flood or a storm. So today we'll combine them, right? As I've been saying for the last 10 minutes, right? So we'll uh, sensor the, okay, I should probably put this here. Yep. Will the sensors will sense the data, right? Some of the information will be triaged, some of them will be aggregated, and we'll send the intelligence, the data point to the cloud, right? And then the cloud makes a big level decision, right? So if there is an imminent threat, it has a better view of the entire picture, right? So imagine thousands of sensors, right, throughout the field, right? If there is a some heavy rainfall upstream, after a while there's going to be a flood downstream, right? So the cloud computing, just by looking at the sensor data from upstream uh, gauzes, can predict flood downstream with significant speed up, right, with significant lead time. So that's the power of this hybrid system. So this is in a sense a three-layer story, right? So we have to sense the data, we have to triage whatever is not useful, and then forecast, right? So this is the same shape as the most modern environmental monitoring systems, right? So this, you should think of what you are going to learn today, the system you are going to see today, right? And the system that you are going to develop with Mihail this afternoon is a template, right? Is a template of how to do real-time like a real world big scale design, and not just a one-off, right? I mean, we are still going to simulate things, right? And we're not going to deploy the actual sensors in the field, but the way they communicate, right? The way the intelligence is distributed, right? So that is uh, I would imagine that's a real thing, right? And that could be useful if you have to design something similar down the road. Okay, so let's think of what happens, right, when there is a flash flood, right? So and basically try to imagine who contributes what, right? So we want to predict the flash flood as soon as possible, right? And then so every minute of lead time is quite useful, right? So flash floods are very, very dangerous because they are one, hard to predict, right? And they occur very, very rapidly, right? So that's why they are called flash floods. So imagine what happens 6 hours before uh, the storm actually happens, right? So we have the weather data, right? And there is forecasted rain somewhere upstream, right? And then so basically so we can say there's an outcoming storm, so we can say activate storm mode, right, in a sense, to the gauzes, and then increase the sampling rate downstream. Now, so 3 hours before the actual flash flood happens, the upstream gauzes will start to detect a rapid rise, right? And then they will send out alarms. Now, because the downstream gauzes, they haven't detected anything yet, right? The place where the flash flood is going to happen, they haven't still detected anything, right? So they are not sending out alerts, and people are still happy, right? But the cloud can now see, right, what's going on, right? So they saw that enough number of sensors upstream have triggered, and there is a rapid rise. So the cloud will now alert the burst of forecast for every downstream ridge, right? And then if this thing holds, then at least 2 hours before the, because it takes time for water to flow downstream, right? So we save a lot of time, right? And the cloud has a better picture of what's going on upstream. We can get up to 2 hour lead time, right? And we can send sirens, we can send counter alerts and dashboards and so on before the actual event happens. And so hopefully this kind of, I mean, maybe we could have used some figure, but hopefully this gives you some picture of how this thing can be super useful. Okay. All right. So now if we want to build that system, right, we should also think about what each component cannot do by itself, right? So as we said earlier, the gauze cannot see the basin, right? It cannot see the upstream rain, it cannot see the soil saturation, it cannot see the neighbor creek, right? So it's these all these things are invisible because the gauze is sitting in one particular location, right? The gauze cannot see tomorrow, right? So the gauze computing is small, right? I mean, maybe this statement is probably not completely true because you can probably push like tiny ML architectures, right? But in general, right? I mean, the compute uh, power is so small that you can't do meaningful forecasting in the edge device itself, right? So and just maybe just based on the past time series you can do the um, uh, uh, water flow prediction at that particular location, but you can't do system level prediction, right, at the gauss, right? So if you have to use the weather model, you have to use the history, that thing's not going to fit. But cloud also cannot act offline, right? So when the storms cut the communication channels, right, the cloud doesn't get the data, right? Hence, it cannot all of its computing power is going to be wasted because it doesn't have the necessary information to make meaningful forecasting. And the cloud also cannot react in microseconds, right? So the round trip data movement takes time, right? The gauze, if it has some intelligence, it can react immediately, right? But if you have to do all the computing in the cloud, that's not going to be immediate because that's going to take some time for the data to go up and come down, right? So latency, because we are in these systems we are fighting against time, right? So latency is one of the things that we have to really, really worry about. Okay, so what are the concrete outcomes for today, right? So after this session and the afternoon session, you should be able to name the hybrid patterns, right, or the paradigms, right? How people set up patterns, and pick the right one for your particular problem, right? So if you have to choose one of these patterns, right? So so basically the pattern is how does the data move and where the computation is done, right? So that's essentially it, and we'll see some examples. But once you have your hydro science problem, you should be able to pick the right paradigm. And you should also be able to place each computation, right? So things like detection, fusing, right, or filtering, aggregation, right, forecasting, and sending out alerts at the right level, right? So if it's a national level alert, probably you want to do it at the cloud, right? If it's a flash flood at a particular location, you maybe want to do it at the edge. So we'll also think about the communication channels, right? What kind of information goes up from edge to the cloud? What kind of communication happens from cloud to the edge devices, and why both directions are useful. We'll also think about uh, how to design a system that but doesn't collapse when there is some malfunction, right? So you kind of want to make sure that even if one or two devices or communication links go offline, the entire system still works, right? And it knows what has failed, right? So we'll also think about that, and we'll assemble the storm test full edge to cloud pipeline, right? So this is going to be done this afternoon. Okay, so we'll start the hybrid framework. Before this, I want to pause and see if there are any questions. I hope I've been able to convince you that this whole hybrid system is important, right? And it can build very good flood warning system, right? As an example. And now, we'll get into the details of what is a hybrid system and how to build it. Okay, any questions? I'll pause for a minute for a question. Okay, let me open the. Q&A is out. It's Q&A. Okay, no questions so far. Okay, where is the? All right, okay, sounds good. Okay, let's move on. Right, if you have any questions at anytime, please feel free to send the questions our way. Okay, so let's uh, like you know recap, right? So the weaknesses of ACE and cloud computing for this our water basin system, right? So C is the present at one point, right? So imagine the water river system, right? So there are creeks upstream, right? Then the creeks float and then the rivers get bigger and bigger downstream, right? And now pick a particular point wherever it is, right? Who sees the data at that particular point very, very well, right? So edge devices, obviously, right? It sees the data perfectly at instantly, right? Cloud only if the communication channel is there, and then it eventually sees the data. Who sees the whole basin? Edge never sees it, right? And cloud obviously sees it, right? Because that's where all the data aggregation happen. Who can see the future? Okay, not exactly see, but who can see, right? As a forecast model is not really, right? I mean, you can, I guess, to some extent, to some limited extent, right? But not really, really. But the cloud, right? Yeah, you can build models, you can build ensembles, you can build you can do a lot of analysis here. So to some extent, it says what's going to happen in the future, right? Who who can still work through an outage? Yeah, edge devices can, right? That's the whole point, right? So you want to keep some functioning devices at the at the physical location even when there is a failure, right? So cloud cannot if the communication channel goes dark. How much computing is available? Kilobytes in edges, right? And if you look at the modern data centers, right? So cloud is effectively unlimited, right? You can scale up as much as you want. The cost, right? So microwatts, the microwatt level power, right? And a few number of years on a battery. But for cloud, you have to pay per hour, right? So now if you think about this, right? So you can see, right, wherever one fails, the other is pretty strong, right? The edge can see everything at once, the cloud cannot. Edge cannot see the whole basin, but cloud can, right? Edge cannot do forecasting, cloud can, right? But cloud cannot work at outage, edge can, right? You see, right? So there's nice complement. These two are nice complement to each other, and that's exactly enables us to build this layered architecture where we can put the right computing, right intelligence at the right level and take advantage of the both, right? So that's the whole point, right? So today, in a sense, we're not learning anything new, right? Technically, right? But we're just thinking about how once we combine these two systems, we can take the fragility away from any given any of these two, right? And build a more robust system, right? So this in systems engineering, right? I mean, you guys are more familiar with this than us, right? So this is called a complementary failure modes, right? So when one fails, the other is at its stronger, right? And so this gives us the perfect justification for the layered architecture that we're going to build, right? So the takeaway is that we do not want to choose between any of these two columns, right? We want to choose basically each row, we want to choose which one to use based on who is the winner on each row, right? So that is essentially what we're going to do this afternoon. Okay, so right, so the idea of the day is to let each layer do what only it can, right, and build some redundancies, right? So the edge wants the instant and the outages, right? It can detect, alarm, and endure. The cloud wins, right? When it comes to the questions about the basin, the entire basin, and the analysis that can help us predict the future, right? So it will like fuse, forecast, and decide at scale. And the wire, right, the communication between them carries only what the other side is generally going to need, right? And we'll also see maybe you can put some like intelligence in the gateway devices also, right? But usually the insights go up, right, and the guidance goes down, right? So that's how this hybrid systems work. Okay, so now let's think about what information goes up and what information goes down, right? So usually, so imagine the edge senses something, right? And there's an event alert. I mean, it should send out the alerts, right, through the secondary channels as we discussed yesterday. But it can also uh, send these alerts to the cloud saying like, hey, look, I'm sensing something, right? The hourly summaries, right, of the minimum flow you have seen, maximum flow you have seen, average flow you have seen, right? So those things should also go to the cloud, right? And your health, the health of the edge device itself, right? So how much battery is needed, right? Is everything working fine? Those things should go up also, right? And if there is a outage, and if there is a backfill of messages that we're not being able to send earlier, right? So those should also be sent from edge devices to the cloud. On the other hand, right, so what kind of information, right, we should push from the cloud to the edge device, right? So is activate storm mode, right? Maybe increase the lower the threshold for alerts, right? And or increase the sampling rate, right? So those things can be sent from cloud to edge, right? So update detection model, for example, right? So yesterday we implemented some a very naive detection model, right? We had if the level rises before this, or if the rate of level increases rises above this threshold, then send out alert. Maybe you don't want to do that anymore, right? And the one alternative is to drive to each particular each location, right? Now if you think about Mississippi River system, right, you have to travel to I don't know, 20 to 30 states, right? And then update each device manually, or you can do send instructions from the cloud, right, to each of the, I mean, you want to set things up such that you can send the instructions from the cloud to each of the edge devices, right? You can also provide some context, right? I expect this, right? 12 feet of water level by 4 p.m. tomorrow, right? So because cloud can do more sophisticated uh, forecasting, it can send forecasts back to the edge devices, and edge can then compare these against a real-time water flow, or send the accuracies, right? Maybe it's if it's already 3 p.m. and the water level is still 2 feet, right? Maybe it doesn't increase to 12 feet, and it can give some feedback, right? So and think of the cloud as a centralized system where all the settings of the systems, the entire systems live, right? So the cloud can still send a configuration and signed firmware update, right? And we talked yesterday that edge devices, right? I mean, you should expect it to be be physically accessible by anybody, right? So you kind of want to make sure firmware updates and everything is signed, right? And this communication can be easily hijacked by somebody, right, as a man in the middle attack and so on. So you kind of want to encrypt this whole communication channel. Okay, any questions so far? Okay, I do not see any. Okay, all right. So now, right, let's this is our the entire week's experiment in a sense, right? So there is one system, there is one storm, right? And there are three architectures that we can build. We can build cloud only model like we did in Tuesday, edge only model like we did in on Wednesday, right? And the hybrid system that we're going to build today, right? Can this system, right? Can each of these system see the flood coming, right? Can we make forecast? Cloud, yes, right? Edge, no, because you cannot there's not enough data, right? And not enough information to make like accurate forecast, not even enough computing. But hybrid system today will be able to do it, right? Because it will just ask the cloud component to do it. On the other hand, can you detect the rise instantly? Cloud, no, right? Because there's a round trip of data information. The edge has to send the data to the cloud, right? And then the sensor has to send the data to the cloud, right? And then only then you will know, right? Because if your intelligence is only at the cloud level, then there's no way you can see immediately. But edge, yes. And the hybrid today, yes, because we'll ask the edge component to do it, right? So it's a, like hybrid is like choose whoever is winning and decide to ask that particular component. Can it survive the mid-flood outage? Cloud, no, right? As you saw yesterday, right? If you don't have these like intelligent sensors, right? So the cloud is going to be blind for a while, right? Well, like I think you guys simulated a network outage yesterday, right? So there were two edge devices. One was the smart one. The other one was like only collecting data. And the one that was only collecting the data could not send the network, could not send any alerts, right, or any data uh, to the cloud when the network out was out. Moreover, that because that this Gauss design were too simple and it didn't even have like backfill, all those messages, all those data points were lost, right? So we didn't like store them, right? So like cloud, right? So the flood kind of vanished, right? Because we didn't see it, right? But edge only, right? If there is a smart edge device which can do the computation, you can say sense, right? So yes, so we'll like see the mid flood outage, we can survive the mid flood outage, and we can also like send out sirens, right? And today we'll like basically take advantage of the like smart edge device to do it, right? Can you watch the whole basin? The cloud can, edge cannot, and the hybrid system can because again, we'll take like we'll ask the cloud component to do it, right? Can you run on a solar budget, right? Uh, Cloud only, no, right? Because the streaming kind of drained the battery, right? Edge devices because it's smart, right? And does adaptive sampling, right? So it can manage its own battery better, right? And as we'll see today, like we can still take advantage of it, right? So it's like if the hybrid is like not a like super like magical thing, right? It's just basically taking like advantage of either cloud or edge, right? Based on who does what better. Okay, so now how do people build these hybrid systems in the real world, right? So what are the five standard ways to share the work between edge and cloud? Let's go over them, right? So the first one is like these are the anti-patterns, right? Basically the things that we did on Tuesday and the bad example that we made on Wednesday, right? Or actually even the good one, right? If you don't communicate with the cloud, right, then like you kind of see that the things are not amazing. So the first is the dumb pipe, right? That we say this is the like the very naive, uh, uh, very naive sensor that we have, right? It reads the streams, right, and then it sends the streams to the cloud, right? The device is either a modem, right, with the sensor attached, right? So it only senses and communicates. That's it, right? It dies if the communication channel dies, right, and drains the battery a lot faster, right? On right, so I think it's not Tuesday, we did it on Wednesday also, right? So this like dumb sensor also was done on Wednesday, right, afternoon, yesterday afternoon, and we kind of saw that this is going to miss the flood, right? The cloud isn't going to miss the flood because the edge device like kind of failed, right? The communication channel was gone and nothing was stored. Now, you can also like think of the like the smarter gauze that we built yesterday, but it never communicates with the cloud. Imagine that it never communicates with the cloud. Right? So it's fully autonomous, no cloud tier, right? Each gauze is going to guard like on its own, right? And it learns nothing, right? So but it can send the like it can send alerts, right? The water level rising alert. It can send the like water level above certain threshold alert, but it cannot do this to our lead time system that we saw earlier, right? Based on the upstream data, we can see that we can sense that there's going to be a flood downstream, right? These systems cannot do that, right? So it's going to be a lonely hero right? Who can work, but it's a local hero, right? It doesn't translate intelligence, right? So to the entire system. So, most real, if Internet of Things failures are based on one of these two ditches, right? So the five, different patterns that we're going to see, right, is somewhere between them, right? So that you can take advantage of both the cloud and the uh, edge. So the first pattern is filter and forward, right? So the edge is going to distill the information, and cloud is going to and then send it to cloud, and where the where the cloud is going to remember everything, and then analyze and make uh, uh, intelligent decisions, right? So this is the workhorse pattern in a sense. And this is one we built yesterday, right? So the device is going to summarize its streams and forwards only the story, right? It forwards it decides on the sampling rate, right? Decides on what's important, right? And then only sends what it feels is important to the cloud. Right? Then the cloud is going to store the data, right? Make models, right? And then on based on the distilled feed that's gotten to that the cloud has received, makes visualizations, right? And then shares it with whoever needs it to see, right? So in every few minutes on the edge device, we're going to sense the data, right? This is going to be on device. And then you distill, right? Events, hourly summaries, threshold, crust, and so on and on. And then you forward, right? We saw yesterday, right? Roughly 25 messages a day is enough, right? Most of the times. And then that data is sent to the cloud, and the cloud is going to archive and build models and so on, right? So this is useful when the data is redundant, right? So imagine when things do not change too much, right? So non-rainy season in a water level, right? Things are not going to change much, right? So that and then you have if you don't have this filtering intelligence in the edge device, right? You'll be sending the same information over and over again, right? And it's also useful when the communication channels are weak, right? So, but where you have to but so in creek monitoring systems, right? So this is always the case, right? That the communication channels are weak. Okay. So in a sense that the data that the cloud the edge device the records and does not send to the cloud is still in the edge device, right? Because the real systems have the memory cards, right? And so on, right? So the entire data is still available, right? It's just the the filtering and the distilling of information is about the radio signals, right? Maybe you don't want to send everything right now, right? And not the actual raw data, right? I mean, you still want to save them, right? So you still want to get a really accurate picture of the real world, right? So if you have a real system, but maybe you don't want to you want the devices to live long enough that you don't want to spend the entire battery on the radio forecasts. Okay, so the pattern two is the trigger and burst, right? So it's basically a $5 chip wakes up the supercomputer, right? So here basically the edge device is looking for the trigger, right? And when the trigger is met, right? So there's a trigger message to the cloud, and then the cloud starts doing something important, right? So here the edge event is basically a starting gun, right? One alert from the gauze triggers the cloud to spin up a series of compute, right? Maybe it then it activates everything in the system, and the all edge devices and the gateway devices also wake up, and then do some rapid sampling, maybe, right? Send all those rapid data to the cloud, and then the cloud makes a decision whether to send the alert, right, to everybody, or go back to idle, right? So that you can think of the trigger as an upstream rapid rise alert, right? So if there is a sensor that's way upstream, and there is a rapid rise, right? So this is only a 60 byte of data from the microcontroller, right? It arrives in the cloud, right? So it's event, right? Not a schedule, right? So it's not done every minute, right? So it's like only something if there is a trigger that happens, right? And then the compute starts. Once the cloud gets it, right, the cloud will then because it's elastic computing, right, it will grab a 32 core machine, right, and then runs a nowcast for the entire basin, right, based on the new alert that it has gotten, right? And then it publishes the forecasts and then releases the course, right? So because this the computing is only happening, right, as necessary, right, as we receive the trigger, right? So the total cost is pretty low, right, rather than keeping renting a large machine, right? So the cloud is going to rent or is going to create an instance whenever it's necessary, right? So the total cost of the system stays low, right? So the next is train up, infer down, right? So the data goes up, right, from the instance to the uh, sorry, from the edge device, the sensors to the cloud, right? So the cloud is the edge device is going to summarize the events, right, and then accumulate, and then the accumulate into the training archive. The cloud will then train a big machine learning model, right? Now we already know that large models cannot stay in the edge device. We'll shrink them, right? Quantize and prune, right, into very, very small model that can actually live in the edge. I mean, maybe not really on the edge, maybe on the gateway device, right? So, based on our paradigm yesterday, which is which has a Raspberry Pi, right, for example, right? And then this new intelligence at either at the edge or the gateway device, right? So that it's going to do meaningful computation at a local level, right? Which is quite interesting. Adaptive command, right? So the cloud makes the edge more vigilant in a sense, right? So the cloud see what, right? No gauze can see essentially, right? Uh, so it can make forecast, it can make upstream alerts, it can make the basin filling, right? And so on and on, right? So it can make prediction about every point in the water, like in a river system, right? And then then it tells to the edge devices, right, when it's quiet mode and when it's the storm mode, right? If it's a quiet mode, the edge device is going to sample every 15 minutes, for example, right? And then the rise alert at 1.5 feet per hour, right? You report out hourly to the uh, cloud, and then basically you are not wasting energy. But storm mode is why we are saving the battery for, right? So here it's okay to spend, right? So now once the storm mode is activated, right, so the edge device is going to sample every minute, right, change the trigger, right, and then increase the frequency of the report. So there's a question from Hassan. When we do nowcasting or forecasting on the cloud, do we use a trained model or do we train a new model every time we obtain a new data? What is often used in operation? So usually there is a trained model, right? So you kind of have this historic model, right? Like historic data, and then you train bunch of different models and do some validation and so on. And then one model is deployed, right? Now the next data comes in, and based on that new data you are making the prediction, right? So imagine all your historical data is training data, right, and the new data that arrives is your test data, right? And on the test data you are making the prediction. Hassan, does that make sense? Okay, I'll mark this as answered. Okay, all right. Okay, let's move on. Uh, right. So the next pattern is the gateway tire, right? So here the intelligence is pushed to the middle architecture, like the middle computing devices, right? Between the fleet and the data center is there is a a gateway device, right? So that kind of talks to the a group of sensors in a nearby device, right? So if the sensors are using ROFA, there has to be a radio aggregator, right, somewhere in the vicinity, right? So they have the radio signals. So ROFA has a range, right? What we said, like 15 to 20 kilometer yesterday, something like that, right? So it's not talking to the cloud directly. So there's going to be some device that sits in the middle between the edge and the cloud, right? So that device can aggregate the cluster, right? So basically, like so 10 gauzes speak to the gateway, and then that's going to aggregate all the data and then send one link to the upstream, right? It can run mid-sized logic, right? It can do cross-gauge level checks, right? Basically, it's a cloud edge hybrid in a smaller scale, right? So with only 10 edge devices for sense, for example, right? So it's a model that's too big for a chip and too local for a cloud, right? So it can run some small things, right? So even when the communication link between the gateway and the cloud goes offline, it can still hold the fort, right? So it can still send signals, it can still send SOS and so on. And it can buffer everything because this device is going to be a lot more powerful than the system that the device that sits in the water, for example, right? Or sits in the bridge, right? So they're you can have a disk there, right? And the disk can store a lot of these messages. Right, so this is the basically summary of the five patterns, right, on each line. Filter and forward. The flow of the information is from bottom to up, right? The gauze is going to distill, and the cloud, basically archives and models, right? So this is not a very useful thing for a flood forecasting system, right? I think um, trigger and burst also same, right? Only goes up, right? So an edge event summons the elastic cloud compute. Train up, infer down, both the cloud learns, sunken model deploys to the fleet, right? So there is communication on both direction. Adaptive command only sends based on the cloud cloud's forecast, right? Based on other data sources, it changes the commands to the gauzes that live downstream. And then gateway tier, right? So where there is communication, right, from the gauzes to the gateway device, and then gateway device to uh, the cloud device, right, and vice versa, right? So that, but here the most important thing is that there is a local brain, right, which aggregates, fuses, and holds the fort. Okay, there were some questions, and okay, so this was mostly about Jetstream 2 account. Okay. All right. All right. Sounds good. So maybe this is a good point to take a break, right? Uh, and I can wait for a few minutes if you have a question. If not, we can take a 10 minutes break. And then we'll talk about how do we design our pipeline for today. Okay. If not, let me pause the recording and then recording. Okay. All right. Everybody, welcome after the break. Oh, sorry. And please, if you have any questions, please keep sending them our way. We're happy to take your questions. Okay. All right. So now, let's think about an example of an early water monitoring system, right, end to end. So, so there, there is a fleet of edge devices, right? And this USGS system is kind of similar to this, right? As we'll see later, and also the Iowa River system monitoring, IFIS, that we talked yesterday. So there is a fleet of edge devices, right? So these are smart gauzes on breezes, on some side of the rivers and so on, right? So this will sense, this will detect, and this will produce an alarm, and they will do they will endure the environment, right? Because they are the ones that are really out in the world. And then there is a uplink, right? Transmission, right? So typically done through the radio LoRa channel, or cellular events, right? So we'll send the summaries, right? We'll send the health summaries of the devices as well, which we are calling heartbeats. Then, the cloud brain, right? So, Jetstream 2 that we're using right now, right, is going to ingest, fuse, right, make the forecasts, and then decide. And then, there is this is sent, this information is sent to the, maybe to the alarm system, right? Sirens, the county level EMA, public dashboards, and so on, right? And then the cloud might also send some information to through the instructions, right, uh, to the fleet, right, where they update their protocols, right, or change the intelligent models that they are currently storing, right? So we kind of want to remember that in real-time systems, right, every link is going to carry traffic both ways, right? And data and insights up, and forecasts and configurations down, right? So if you ever see architectural diagram of this kind of sensor network, right, where the arrows point up, right? So immediately think okay, so this is a fragile system, right? Like we did on Tuesday, and we saw how the sensors can go blind, right? How the cloud can go blind if the communication channel fails. Okay, now let's think about where to put the computation, right? So we are aware that this hybrid system is needed, right? And hybrid system lets us take advantage of both the edge and cloud computing paradigms, right? So where should we put the computations, right? So who should sample the river? Obviously edge, right? It's physically there, right? And nobody else can do that, right? So at that particular point, right, in the river, if you want to measure something, right, the cloud edge device should do it, right? Who's going to detect the rapid rise? Also edge, right? Because it has to be rapid, right? It has to be instantaneous, right? So the edge device has to detect the rapid rise. Who's going to buffer the outages, buffer the messages during the outages, right? So it can be done in the edge, like we saw on Wednesday, right? The smarter gauze that we simulated was able to store the messages when the network was out, right? And then we were able to send the messages later, right? Or it could be done at the gateway devices, right? So where there is a hard disk, right? And then the disk can store information long term, right? And then once the network is out, network is back up, right? So these messages can then be sent to the cloud. Who should fuse the basin picture, right? Who should see the entire, who should try to make prediction about the entire basin? Cloud, right? Because for that, right, to create the big picture idea of the entire basin, right, we need data from every gauge, right? We probably also need a national water model forecasts, right? We probably also need the weather data and so on. So cloud is the right entity to handle this, right? Who should we trust to forecast 6 hours out? Also cloud, right? Because we can build we can build and train and store heavier models there, right? And these kind of computations are never going to fit in kilobyte, right? So cloud can we should probably trust the cloud to do it, right? We should sound the local siren? Edge, right? But we should send the data to this national dashboards? Also cloud, right? So as you can see, depending on depending on the task that is critical for this sensing the water stream, the duty either falls under the it's either it's best to either choose the edge or gateway or the cloud, right? So we kind of have to be aware of the task that we are handling. So there is a question from Mayuran. If you were to install gauzes in a flood prone catchment area that is currently ungauzed, how would you set it up for early warning, location of smart gauzes, cloud setup, etc.? Would you install smart gauzes throughout the river or just at the flood prone area? That's a great question, right? So it's kind of the you want to do two things, right? You want you want to hit the critical areas, right? Because that's so if you know, right, which areas are prone to floods, right? And I would first install the edge devices there. But then you also want like entire coverage, right? So the floods, waters flow downstream, right? So one event at one place triggers another downstream, right? So you also want like entire coverage. So you should compute, look at how much budget you have, right? And how much coverage you get, right? And then based on that, you determine the location of the smart gauges, right? And then the cloud essentially, now if it's a small system, right, then the cloud can sit nearby, right? If not, you also need these gateway devices, right, which is going to talk to the edge device through either cellular links, right, or through radio signals, right, and so on. And then that device is connected to the internet, and then that is that sends information to the cloud. So the next question by Nischal is, smart gauzes rely on USGS data. How can we use them to predict flash floods in urban areas? Not really, right? So USGS data is collected by smart gauzes, right? So imagine it's we're talking about the world where USGS doesn't exist. How do you build a smart USGS network, right? So that's what we're talking about essentially, right? But in a world like smart USGS data are is already being collected, right, by a hybrid cloud data system. Let's imagine that, right? And I will answer your question in that context. How can we use them to predict flash floods, right? Produced by a short duration intense rainfall events in urban areas and roadways that lack measurement devices. Any idea? So, that's a great question, right? So this is where modeling comes in, right? So, from your USGS data is telling you, look, right, the water levels is rising rapidly and nearby, your city, right? Maybe then you can use your your cloud, right? Then can take geographic of your area, right? Any flood history, right? And so on, and make some model that can make the prediction, right? So this is a great example of of a project that you can do for your capstone, right? So here example, here I don't know exactly where the USGS data is near Iowa City, right? I can take that, right? And then I can then look at the geography of Iowa City, right? And one of the signals to my flood prediction system in Iowa City could be that USGS signal, right? Okay. All right. Thanks for your questions. All right. Okay. So now, what are the decision level, right? What is the time resolutions of different decisions, right? So if you're thinking about millisecond level decisions, right? So these are device rules, right? Threshold, rate of rise, right? Sending out sirens and so on, right? What happens at the seconds level, right? Fleet messaging, right? So the cloud can send messages to the entire fleet. The entire fleet can aggregate the data and send it to fleets send the data to the cloud and then they aggregate, right, or the edge device, and the alerts go up, right? And then the storm modes, the cloud can then activate storm modes, right? Maybe faster sampling and so on. At minutes, right? So cloud can do nowcasts, right? So maybe it takes 5 minutes to run a inference on a large language large model, right? And then the cloud produces those forecasts, right? And then sends the forecasts back to the basin, right? At hours, right, you can do ensembles, right? You can produce the national water model level forecasts, right? And gives us basically the horizon for the planning, right? Should we send alert on the NWS, right? Or should we send flash flood warning to a local area and so on, right? So those decisions can be made, right? At years level, right? So you can train the model, right? You can think about how to improve the system, the entire basin system, right? Should we update the location of the sensors, right? If we miss something, right? Should we change our machine learning models, right? Should we change our forecasting model and so on? Should we change our communication links, right? So it kind of at years level you can do this kind of analysis, right? So there is a real basin system and floods happen from time to time, and you are trying to build a system that collects the data in real time and tries to predict floods before they happen, right? So you have to update them, right? Because maybe the model and the placement of the sensors and the communication links are not right the first time, right? So you might want to update them from time to time. So there's a question from Francisco. How do cloud systems handle bad data outliers, right? That possible generates a false alarm and latency when using automated alerts. That's a great question, right? So one, right now we should make sure that so we should we'll see, right? You should keep checking the health of each edge device from time to time. And that's one. That's a precaution, right? So that the cloud knows which data to trust. The other thing is you should always run outlier detection, right? You should always try to find out uh, faulty systems, right? And in the flood system there is the cost of making false negative and false positives are very different, right? If there is no flood but you say flood, right, and send out forecasts, what's going to happen? People are more cautious, right? I mean, you don't want to do it every time, but people are more cautious, right? And so on, right? But if there is a flood and there is you don't make any forecast, right? I mean, people die, right? So there's imbalance between these two errors that you can make, right? That a model can make. So you also want to think about that, right? So when you you would want to predict the flood when there is no flood than not predict flood when there is flood, right? So you also want to take that into account. Okay, all right. Let's move on, right? So where does where do the data live and how do they move, right? So let's think about that for a little bit. So there is every minute, right? So there's a raw readings on the gauge's SD card, right? And then the ground truth always stays there, right? So that can be maybe when things are good, right? And there is no risk of flood, maybe based on the weather system, you can then transmit the data, right? And then that sun is out, so the solar is going to charge. You can plan for those things. So within seconds, right, events and alarms can go up instantly, right? So there's a tiny urgent priority, right? So at the hourly level, right, so the summaries can go up, right, from the edge device, and the cloud basically updates its working picture, right? So the cloud is intelligence is running, and maybe based on the summaries of the edge devices, maybe it's thinking, okay, the water levels rising, right, at 2 or 3 locations upstream, maybe there is a chance, right, that water level becomes slightly up downstream, and so on at every day or on request, right? So you can get full resolution history backups, right? When the link is cheap, right? So why we're saying night? Because in night the demand on the network is less than during the day, right? So maybe every night you can schedule to send the entire backup, right? And forever, the cloud is going to archive, right, and store the data, right, and then basically collect the basin's memory, and then try to find out try to update the model so that it's more accurate, right, and runs better. Okay, so now we also have to think about the failures, right? So in real-time systems, failures should always be expected, right? So all four of these things is going to happen, right? So once you build it, right? So it shouldn't be a surprise, and a good system should anticipate it and plan for it, right? So if a gauze dies, what should your system do? So neighbors, right, neighboring gauzes, right, and the cloud can interpolate it, right? So you can basically, based on the neighboring data points, you can possibly interpolate it, right? And somebody should know that the gauze has died, right? And they should drive to the physical location, right? And try to fix the system, right? But the system should detect that the gauze has died, number one, right? Somebody should be alerted, number two, and until it gets fixed, there should be some intelligence, right, that kind of still works, right? Maybe it's slightly less accurate, but you can still figure out, right, what data the gauze could have sent. If a link dies, right, similar, right? So you build a local autonomy, right? So the edge kind of takes over, right? Sends its own alerts, right? Like the messages that you'd have sent on the buffer, right? And then fire sirens, right? Until and then the record hits, right? So you still want the system to work, right, locally, even when communication with the cloud dies. when a gateway dies, right? I think it's similar, right, to a gauze dies, but like now instead of not getting data from one gauze, you're not getting from 12 or 10, right? So then like the gauzes will then fall over to the cellular backup, right? So communicate through the backups if possible, right? If not, take the local autonomy, right? Like we show you guys how to do yesterday, right? And even when the gateway dies, right? So imagine county level data is lost, right? It should act as a convenience issue, right? Not a coverage issue. If cloud dies, right? I mean, rare but real, right? So maybe you want to have a backup system, right? That can take over. But also, if that dies, right? So what are you going to do? So I'm sure, USGS and so on, right? We have multiple cloud systems, right? As a backup, right? So if one machine dies, the system doesn't even feel it. I mean, I'm sure the technicians get alert and so on, and they will try to put the system back up, right? But the website and the data collection and the pipeline still is running, right? So there should be some redundancy everywhere, right? But let's say even if the redundant system fails, right, that can still happen, right? But the fleet can still keep sensing, right, alarming, right, buffering, right, and once the system comes, all the buffers will go up, right? And if there is a flood, right, the local systems can still send out SOS and alerts and so on. Okay, so how do we go from detection to the human decision, right? A warning system is just by what humans do with it, right? Because at least nowadays, right, humans authorities have to make the decision, right? I mean, there has to be somebody who takes action, right? So different audiences need different speeds and different confidence, right? So your system should produce make detect events or forecast event with some confidence, right? And the hybrid basically gives an audience its own path, right? So that we can do a bridge siren, right? So this is edge triggered, instant, right? No confirmation needed, and people in the water's path move first, right? So county or emergency managers, right? So do send a county level forecasts, right? So this probably has to be confirmed by the cloud, right? So the alert plus the burst forecast is made, right? And we'll we should identify, right? The system should identify which roads are affected, when, right? How much of the floods are going to be on each of the roads and so on, right? So these things have to be communicated to the public. If you are trying to send forecast to the public transports, right? You fuse the basin picture, right? You measure every gauze, right? You forecast the bands, you make the context, right? Kind of IFIS that we saw yesterday. Okay, so now how do the messages move, right? Let's talk about that. So we said yesterday the edge devices talk via MQTT protocol, right? So the protocol basically is a publish subscribe protocol, right? And it's extensively used by Internet of Things. So basically the devices publish tiny messages to a named topic, right? To a broker. Anyone that is interested is a subscriber, right? Not everybody needs to subscribe every message, right? Not everybody will publish every message, right? So, and nobody needs the other things, physical addresses, right? So what are the possible topics in our system, right? And some example. So it could be basin in Iowa, go 7, sent an alert, right? Or summary or a heartbeat, right? Or configuration, right? Is sent to activated to be storm mode, right? Now it's a basin Iowa in GAU 7 sends an alert, right? The other edge device do not have to listen to this, right? So maybe the cloud or the local gateway device is going to subscribe this, right? But if it's a configuration that says activate storm mode, then all the edge device should subscribe to it, right? And it's probably published by um, the gateway device, right? So what are the one advantage of this protocol? It's very light, right? So there's a very few bytes of overhead, and designed exactly for like these thin links, right? So that we're like talking about when the communication channels are like poor. So this all system is also like this system is decoupled, right? So the gauges do not have to know the cloud's address, right, and vice versa, right? And the broker, right, which is the like probably a gate device, kind of mediate between everything, right? And the delivery kind of promises, right? So QoS levels, fire and forget for summaries, right? And guaranteed delivery for alarms, right? So for summaries, like you'll fire, right? You'll like and then like if somebody got it, got it. If not, you'll forget it, right? But like if there is an alarm, right? If there is like some security threat, right? Then like there is a like so you'll send keep pinging until you receive acknowledgement, right? So this is kind of like fire and forget is like the protocol that runs a video chat over the internet, right? And guaranteed delivery is like when you like download something, right? Or like load a web page, right? So your local computer has to say to the server like, look, I have received the web page, thank you, right? Until your like browser says that back to the server is going to keep sending this. Okay, so how does the message look, right? So just an example again, right? When a link is priced by the byte, right, and powered by the sunlight, you kind of want to be careful about what kind of message is sent, right? So this is an like alert packet from yesterday's simulator, right? That you guys implemented. So there was a gauze ID, which is like 2 bytes. There is a message type, right? It's either alert, summary, heartbeat, or backfill, right? It's just 1 byte, right? It can be 000, 00010, right? And so on and on, right? So there's like not that many options, right? If you're very, very careful, right? If you want to like, like code everything from scratch, you can probably do it in 2 bits, right? Or 3 bits, but maybe you don't want to, right? So this is okay, right? And then there's a timestamp, right? 4 bytes. You want to say which kind of alarm you're sending, either it's a stays or a raise right, right? That's just 4 bytes, right? And then the battery flags, right, which is the health telemetry, right? You always want to send them a checksum, right? So this is like basically to check whether there was like something got flipped during transmissions, right? So again, right, communication channels are like faulty at times, right? The bits keep flipping, right? Like because like systems are not always 100% system like correct, right? So you kind of want to have a checksum, right? So that kind of guarantees that this was actually the message that was sent, and this is the message like the correct message was received. Now like once the all of these messages are received in the cloud, you kind of want to like aggregate them, right? So like for example here like gauze 7 alarms, gauze 9 is quiet, gauze 4 went silent an hour ago, right? And the radar system says heavy rain upstream, right? So what should the cloud do, right? It kind of want to first assemble the basin state, right? Takes every gauge's last word, right? Weather data, right? National water models, number in a single map, and you kind of want to cross check the crowd, right? So this is kind of like the Winston's lessons applied, that you kind of like there is a dense network of cheap sensors, right? And you kind of want to sanity check, right, against the gold gauges, right? And treat silence as a data, right? So if there is no message, then you kind of want to flag it, interpolate, right? So maybe the device is down, right? So you kind of want to handle that correctly. And right now, you also want to do like produce predictions with confidence, right? One alarming cause is a question, right? Right, and then like a few with the radar is like is like probably like the accurate picture of what's really going on in the real world, right? So you kind of want to like make sure not all forecasts are equal, right? So depending on like what kind of data the cloud gets, right? So you kind of want to like build a confidence system, right? So there are different machine learning models that produce confidence, right? Or like you can like also like build rules based on like how you're going to treat your forecasts. So now, like, how do we close the loop, right? You want to sign everything, right? If you want to update things in the edge device, right? You want to sign everything and you want to implement that logic, right? Basically yesterday's rule on edge device, right? That all edge devices are physically accessible by some malicious agent. You should think like, like that. So you want to like, make sure that only cryptographically signed config and firmware run on the machine, right? Nothing else runs. Roll things out on stages. New model to 5 gauzes per week, then 50, right? Never at once, because if the model is faulty, then you don't want to like, ruin the entire system. Right? This is like, how real-time deployment should always be done, right? You roll it at stage, right? Because you don't know. Just because the system works on a local computer does not mean it's going to work on the real field, right? So how does this coding work? I mean, like, you will have a simulator like the one Mihail, like, shared with us yesterday, right? And you will implement the logic that you did yesterday, right? And you will see that in simulated world, the logic works. Then you will roll it out on the real world devices, right? But just because the logic worked perfectly in the simulated device does not mean it's going to work, it's going to be fine in the real world, right? So you kind of want to take like, you don't want to like, jump in the river with your both the feet, right? You want to take one step at a time, right? To kind of sense how deep the water goes. That's exactly what we're doing here. Always keep the escape hatch, right? And like, there should be backup, and you can roll back to the last known good version, right? Any update can break things, so you should always have a system to go back. Watch for the canaries in the coal mine, right? If the staged gauzes alarm differently than their neighbors, then you should stop the rollout, right? Then that means something went wrong, right? So you should like look out for these things always. Okay, so now who watches the watchers in a sense, right? I mean, you should always monitor the like health of the edge devices, right? So that's always a good system, because if not, then like essentially like you may be like because of some faulty things, right? You could be the edge device could be sending the wrong numbers, right? Always gather the heartbeats, right? Every gauze should say alive on schedule, right? And the dashboard should say like silence in reds, right? So that the system knows that some machines have died. So there should also always be like health telemetry, like battery and solar trends, right? So they should like be sent and should be replaced before it dies, right? And not after. There should always be data quality flags, right? Drifts, spikes, right? Any disagreement with local labels, right? This should always be flagged automatically, right? Bad data, right? At times is worse than no data, right? Because it can like, lead to the wrong conclusion. And there should always be drills also, right? So it's like a fire drill for the system itself, right? So you kind of want to like regularly inject some synthetic flood, right? And see what happens, right? Does the entire system work or not? Okay, so now let's look at like how the real things are built, right? So like this is the uh, uh, in a sense, the entire America's like flood forecasting system is a hybrid sense, right? So there are like this USGS system has like 11,000 gauges, right? These are like field hardwares, telemetry, and buffering. They are like pretty smart systems, right? The model is the national water model, right? 2.7 reaches forecasts every hour in the cloud, and then these are like interpreted by the river forecast centers, right? So by humans and other models, and then they then like give the official forecasts, and then this is then sent to AWS, right? So sent out as like warnings to counties, sirens, right? Now it also shows on Google, right? I think they probably scrape NWS, and also shows on Google Maps, right? If you are trying to drive. So it's like, a week ago, I had to drive from here to a nearby town, and it said that, one of the roads has a flood flush warning, right? I mean, the weather was clear, right? But still, so it was like a good to see in real time. Okay. So, right, from Iowa's example, right, IFIS, you probably have used this data, right? So this is also a hybrid end-to-end system. So we kind of like, sample the data from Iowa Flood Center, right, yesterday. So here we have like, 250 plus solar bridge sensors doing on-device housekeeping, right? And then they like, keep sending messages to the centralized cloud, like, as needed, right? So basically frugally trying to save the battery. So the cloud is like statewide flood models and inundation maps computed centrally. And so the fusion happens, based on IFC sensors, USGS gold gauges that are in Iowa, right, in the same river systems, NWS forecasts, right, and based on all of these, we will one coherent picture, right, and so the data is delivered to IFISI or floodcenter.org, right. So if you get chance to talk to Ibrahim tomorrow, I'm sure he was heavily involved in building this system. Okay. How much does it cost? Right? The fleet, 10 smart gauges, right? It's powered by sunlight, solar powered, right? And batteries are going to leave the hardware, right? And so there is a inherent cost of upfront cost, but how much does it run to how much does it cost to run the system, right? So the cloud ingestion plus fusion, which is always on, approximately you can do it on two core service, right? Between the storms, that's going to be like 48 credits, right? That we're using right now per day. The burst forecast per stream is per storm event is going to cost, you probably need 32 cores, right? For 4 minutes, and then you release it, right? So approximately 2 credits, or say let's say 10 minutes, right? Increase this to I don't know, 5 credits, right? And see, you may want to run dashboard and archive. This is also going to be always on, right? So this is going to be one small virtual machine because it's just a website, right? And the object storage. So you don't need anything fancy. So that's 24 credits per day. That's so for full storm, right? It's about 26 credit, right? That's 13% of our 200,000 credit accumulation, right? So it's not too expensive to run, right? I mean, it costs real money, but if you are smart, right, it doesn't cost too much. And building this such system is feasible. When you shouldn't use the hybrid system, right? If you have only one sensor and only one study, right? No need, right? Maybe a semester long project on a single gauze, right? Just stream it to a notebook, right? No need to build a cloud, right? And so this big heavy machinery is not needed. If you have a perfect infrastructure, right? A monitored wire at a research station with fiber and power, right? It's also not needed, right? Cloud only is fine. If there is no urgency, right? So a monthly groundwater levels, right? There you don't need a age level, urgency, right? So just a data logger, right? And regular, uh, updating to the cloud is fine. No one to run it, right? If the hybrid system is going to be ongoing operation, right? So if nobody wants it, right, then just build simple, right? So just have a cloud system. Okay. Now, right, so some mental things to keep, right? So let each layer do what it only can and what it does best, right? So that's the best way to design the hybrid system. The communication is a two-way street, right? Usually insights and data go up, right? And then instructions and guidance come down, right? So there are five different patterns that we covered, right? So basically use them, right? Instead of trying to reinvent them, right? So unless you find something very, very unique and none of these five systems cover them, right? But usually, these five systems are comprehensive enough, right? Because they cover all, most of the use cases. And you always want to design for the failure, right? And failure in a hybrid system should be expected, right? Because there is multiple failure points, right? So and so you kind of want to make sure that even when there is a failure at each level, right, the edge devices could fail, the gauze the gateway devices could fail, the cloud device could fail, right? So even whenever whatever fails, the system should keep on working, right? And as we said earlier, the national systems and also local systems like Iowa systems, right? They're built exactly this way, right? And the thing that you're going to code this afternoon in a simulated environment is also going to be in this way. Okay. So what are we going to do this afternoon? We'll first, yesterday we only had one sensor, right? One gauze. Today first, oh my God, why is this keeping moving? So today, we'll keep launching the fleet, right? The five smart gauzes from yesterday. So instead of one, we'll have five, right, on a storm running down the basin, right? So the five sensors will be placed in different places in the storm in the basin, and they will simulate a storm, right? And we'll build a cloud brain, right, which is going to ingest all the services, right, and it's going to be have a live basin board, right, and there's going to be trigger and bursts, right, the upstream alert fires, right, based on Tuesday's nowcast, right, and every region parallel, and we'll push the storm mode down, right, and measure basically activate the urgency, right, in the edge devices. So I'm looking forward to this, right, to see how you guys will implement this whole thing, right? So in 3 days, right, this is what we did, right? Built an early warning system from the riverbed to the forecast, right? So today's thing will tie the entire thing, right? On Tuesday, we learned how to rent a supercomputer, right? And then create a live data and then the forecast based on that. On Wednesday, we thought about how the gauze thinks, right? Takes powers, right? And wants a network, right? Today we'll mix this up, right, to build a complete picture. Okay. So your projects on this plant, the hub is going to stay up, right? Maybe until tomorrow, right? And then so but you can still running your notepads, right? You can take all three notebooks, right? You can fork them. You can edit them, right? And you can change them based on what you need. The credits are budgeted, right? So the for next week at least, we'll allocate some credit to each of the groups, right? Once we form tomorrow, and then just want to let you know that we're on call, right? And on week two, right? So any questions that you have, we'll try to help you. Okay, that's all I have prepared for today. So I'm going to stop here and take some questions. Okay, so there's a question from Asan. One of the issues I have faced when working with aquatic sensor data is that the sensor can sometimes be buried in the river sediment after a high discharge event, leading to a gradual deviated pattern in the data. How can we involve such issues in the cloud edge pipeline? That's a great question, right? So this is the kind of the so you right so you kind of want to sense that this is happening automatically, right, in your clock. Imagine you have a sensors like this, right, five of them, right, and one of them gets buried in the river sediment like you said, right. So how do we automatically take it, right? Maybe the pressure data is going to be very very different, right, because now it's maybe the pressure is way too high, right? There's a river above you and then you are under the sediment, right? And maybe the device doesn't get charged anymore, so the health the battery goes down, right? So you kind of want to detect it, right? That's the first thing. And then once you detect it, right, I mean you should send out the alert, right? And maybe based on the other readings of the nearby events, nearby devices, right, you kind of want to impute, right, so that the whole system keeps on going, right? So you can't do much other than detect, right, and keep working without this data, right, until someone can go and fix it. Okay. Some other questions? Okay. If not, I can stop sharing, right? I can also pause.
All right, so for those of you who came late, and if you don't have access to the IP address, I just pasted it into the chat. All right, so this is the season finale, basically. Today we're going to put together everything we've done over the past couple of days. So first of all, let's have a small review of what we have done so far. So first of all, in the first day, we introduced basically the cloud. We introduced how to interact with the cloud, how to get data into the cloud, how to store it, how to process it in the cloud, and finally how to make it human readable, basically like export it from the cloud. The second day, we built some gauges. Basically, we simulated edge devices. So we first simulated a naive one, which, as we saw, it was draining the battery pretty fast. And then we made a smart design, which operated way better. Okay. Today we're gonna put them together, basically. So we're gonna have a hybrid pipeline. So we're gonna have a gauge fleet, basically a set of different gauges, and a cloud brain, which is basically coordinate with these gauges. Okay. So let us start with part zero. If you have any problems with connectivity, with accessing Jetstream or the notebooks, or if you don't have access to the notebooks, please let me know in the Q&A. Okay, right. So let's start with part zero. So as Dr. Bijaya presented this morning, we were going to be simulating a storm. But this time, the storm is not going to happen just at one position in the river, but it's going to happen over a whole basin, basically. So we can think of it like this. On one side of the basin, there's the headwaters. Basically, that's where we can say that that's where the river comes from. And on the other side, there's going to be a town, basically. So what we want to do is actually create the early warning flood system. And how we're going to do this, we're going to basically try to predict as soon as possible, or like detect as soon as possible, that the flood has happened close to the headwaters before it reaches the town. And if you remember from yesterday, even when we had just one smart gauge, we would get, if I remember correctly, around 3.3 hours of head start before the flood actually reached the town. But again, this was just locally. So today we're going to see how to interface with the cloud so we don't just sound the local alarm. Okay. So again, the storm we're simulating is the same one from yesterday. It's basically the same formula, and the function that we're going to create is the same as yesterday, but we're going to have one small change. We're going to add this offset min, basically, over here. Now, what it does, basically, we can think of it like this, like the whole flood is basically shifted later by offset min minutes, right? And also everything now is in minutes, right? And the only, I think, problematic function is mp.interp, but it's the same one from yesterday. So if you have any questions regarding it, please let me know. I can answer them. Right. Okay. Yeah, the storm has the same shape. So again, we have a huge spike, a daily wiggle, and some noise, basically. Okay. Now, this is the key line, this one over here. So basically what we're doing here, we're gonna, in a sense, build five gauges. So we haven't defined yet a gauge class in this file, but we're just saying that there are five gauges. Okay, so each gauge G basically gets the storm delayed by 90 minutes. So we don't get complicated. We're not going to do it in meters because we have to take into account the velocity of the river. So we're just going to say that each gauge is 90 minutes ahead of the previous one in terms of the river flow. Okay, so basically gauge zero is going to flood first, gauge one is going to flood 90 minutes later, and so on, basically. So this storm is going to be traveling downstream, right? So basin is basically a dictionary of these gauges, and time is like the shared minute timeline that all of these events are happening on. Okay. So we can calculate basically the travel time from the headwaters to the town by basically just subtracting the number, like subtracting one from the number of gauges and multiplying by the travel, basically. Okay. So if we actually do that, we're gonna get that there's around 7.5 hours between the moment the storm reaches the first gauge and the time it reaches the town, basically. Okay, so now let's plot it. Okay, so as you can see right here, remember yesterday we just had one of these plots basically. We had one storm, but now we can see that each 90 minutes another gauge basically gets alarmed or alerted by the storm, and it looks like ripple waves basically. So we can see that even if, for example, we don't have any brain or anything, the time between the when the first gauge surpasses the flood stage is way earlier than when the town gauge surpasses it. So even a dumb system here could give us some leeway. And we've seen yesterday this was around 3 hours. So we're gonna try to do better today. Any questions so far? Okay. If there are no questions, let's move along.
So Mihail, I think this is the like, single river, right? There are no branches or anything like that.
Yes.
Okay.
There's like a one basin, one river basin, and they start basically in the headwaters and we travel to town downstream.
Okay. Sounds good.
Yeah. All right, now the fun part. So we're gonna basically simulate this fleet. So what's the problem? The problem is, as Dr. Bijaya mentioned, usually these devices use the MQTT protocol. So this is a protocol that's familiar. It might be familiar to you if you've ever used IoT devices. But basically, how it works is just a message bus with a queuing system. So it's like a queuing system from which specific devices read or some also publish or write to it. Okay, so again, the hardware is going to be exactly the same from yesterday. So the oh, someone said something in the chat. Yeah,
Yeah, with
yeah.
that, this
So
code is already shared with all the participants in
yes,
their
yeah,
cloud system. They just have to go to this IP address and click
yeah. They
create
should
link.
have it already. But if you don't, let me know, and I'm gonna reshare the link. Basically. Okay, so where was I? Yeah. Again, we're gonna be sharing the same hardware and this Lambda function. I think you're familiar with it. We just convert from milliampere and seconds to milliampere hours. Okay. So now this message bus basically is gonna be like a stand-in for MQTT, so like a simulation of MQTT. So basically, MQTT, as I told you, is the real pub sub or publication subscription protocol that IoT sensors tend to use. And usually it's just a shared list of time, topic, and payload messages, right? So usually what publish does, it appends one, and messages usually returns everything who's like if you input a prefix basically into the messages, is going to return everything whose topic starts with that prefix, right? So for example, let's say, I don't know, in our case, we can put the prefix or the topic to be basin or gauge, right? If the cloud is asking for any message that has this as the prefix, it's going to get all of the messages that the gauge has published in the basin, basically. So it's kind of like a shared channel model, which will be connecting the edge and the cloud. It's similar. Like we can also have a gateway system or a router that does these things, but for simplicity purposes, we're just going to go with the way IoT does it. Okay. Now, the smart gauge class. So the smart gauge class, it's basically the same one as yesterday, but this time around we stripped some of the attributes and functionality from the one from yesterday, and we're not using inheritance. So we're not making another base gauge class. We're just gonna have this smart gauge class. And again, we have exactly the same it has exactly the same attributes as yesterday. So remember, when it was rising more than 1.5 feet per hour, we would alert, and we would do adaptive sampling. So when it's quiet, we do it every 15 minutes. When it's not, we do it every minute, basically. Okay. Right. So, but this time you can see that the rise alert and quiet every are class attributes, meaning whenever we instantiate an object, like a smart gauge object, like every time we create a gauge using this class, they're always going to have the same constant no matter what, and we cannot change them. basically. I mean, we can override them, but it's like practically we don't do that. That's the whole purpose. We are doing it like this. So now, because this time we don't have just one gauge, we're going to have a fleet of gauges. We're going to assign an ID. So we're going to have GID, which is basically going to be the gauge ID. So we're going to have this will be like the identifier, which tells us which gauge is it in the system, basically. So think of it as a username in a database. Okay. And we're also going to be taking in a bus, which is going to be the shared bus that all the gauges are going to communicate with the cloud through, basically. Uh, right. So the read function, again, is just sensing. Basically, it's like reading, getting the reading of the actual discharge. Now, transmit is basically is the same like energy accounting, so it's like using the same amount of energy per action, okay? But now this time it actually publishes to the bus. So instead of just sending it out or alarming it out or doing, like some local stuff, now it pushes it to the bus, which is gonna interface with the cloud. So this is already part of the hybrid architecture. You see this, like this gauge in itself has some logic that is necessary for it to communicate with the cloud. Okay. So now we can have like different kind of topics, like we can have basin, gauge zero, alert, whichever you want for the payload dictionary, but we got to make sure that the cloud understands these topics. Okay. So flush is exactly the same as yesterday, but this time, so remember flush, basically what it does, it's like when there's an outage, we do a backfill, basically. So we just pop from the buffer, but this time again, we publish it on the bus. Okay. Rise, again, same as yesterday, it's a helper function to let us determine if the river is rising or not. Okay. Now, step is the actual function. Remember from yesterday, it's the actual brain of the gauge. So again, it's almost identical, but with one very crucial addition. So basically, we have a config now, and basically what the gauge does. So the gauge reads its trigger threshold from a config dictionary. Okay, so it's happening here actually, right? And based on this, it's gonna basically update the cloud. Okay, so also the cloud can also update it. You see, so we can have back and forth interaction. Okay, so if the cloud hasn't touched this, basically, it's gonna just take the default. I think I set it to 1.5 if I remember correctly. But if the cloud pushed the storm mode, it's going to take whichever value it was handed. Okay. So this is basically, when we were talking during the presentation that it's actually a two-way street. So the edge sends it up, but clouds tends to configure it down. So it's still the cloud that does the configuration, but we can also have a base configuration inside the sensor. Okay. And now we're going to have two detection rules, the rapid rise and the flood stage, which are exactly from yesterday, and also the stand down and the hourly summary, exactly like in day two. So if you have any questions, please let me know. All right. So we can run this. Actually, did we run? Yeah, we can run this. Yeah, it's just going to print the fleet class is ready. Okay, we have the adaptive sampling, the two rules from yesterday, the summaries, the store and forward, and a radio. And now the logic is able to interface with a hybrid system. Any questions so far before we move to the cloud brain? If you can explain the message bus. Yes. So basically, remember the like when Dr. Bijay was presenting this morning, IoT uses a protocol called MQTT, right? So this protocol What it does is basically think of it as a bus in which messages get stacked on it. Okay. Now, each message has usually three properties. It has a time, the time it came, a topic, like for example, the topic is in a sense a way to make messages, separated based on purpose. Like for example, when you have social media, it's similar to like one is Facebook, one is Instagram, something like that. The payload is the third property. It's basically the actual message. Okay, so for example, let's say the topic is gauge zero. Okay, so and it comes, I don't know, a time, let's say 5 seconds, right? So if that's the case, at 5 seconds, we're going to get a message from gauge zero that tells us, I don't know, there's a flood happening. Okay, so if the cloud is actually looking through these messages and it tries to filter them, I don't know, by which gauge it came from, it can take the topic basically and know which ones actually came from which gauge. Okay, and the payload is going to tell us what is the actual message. Is there an alert? Is there some kind like is the flood coming? Is there a rapid rise that can tell us there's a flood coming or something like that? Why to have done this is basically a simplification of the MQTT protocol, in which we just publish to this bus, and the messages can return all of the messages that are on the bus. So the cloud can filter it. Okay. Someone's asking, are these system architectures for these notebooks? System architectures. If you mean this like is this a real system architecture, or like is this how system architectures tend to be in a cloud? Yeah, this is how basic cloud protocols and like gauges tend to be programmed. Of course, like most probably for microcontroller gauges, you're not going to use Python and object-oriented programming. Most probably, it's some form of C++, like or some other form of. It's actually called edge computing. So, yeah, possibly to aid understanding. Yeah, so basically, if you attended the lecture that Dr. Bijaya gave today, there was an actual real protocol called MQTT, and that's the one we're trying to replicate here. Yeah. Any other questions? Yes, thank you as well. All right. There are no other questions. Let's go to part two. Okay, so now. Oh, someone has a question. I have a confusion that why we couldn't implement this message bus earlier in the edge computing. Very good question. Okay. So yesterday there was actually no need for this bus. Why? Because we just had one device that was basically like it was sounding an alarm. So for example, there was a gauge that was connected to an alarm system. So basically, when anyone passed by the river and this alarm was turned on, they would hear it. But now, if when we have multiple gauges, and these gauges need to talk, not they don't talk with each other, but they need to talk to a centralized computing system, which is the cloud in our case. There needs to be some form of queuing for these messages. So, of course, like if you're familiar with networking, usually there are like when you have different computers, how it's usually sent. You send a message, through a line as a packet or something, so these packets get queued, like you have an actual queue of messages. And usually there's different, like if you've dealt with data structures, the different way to do them, like you have FIFO, first in, first out. You can have priority queuing and so on. So basically what this bus does, think of it as an aggregator of messages, and the way we process them is depending on like the central processing part, which is going to be our cloud brain. Yeah. So basically, in simple words, we need the bus because we have multiple gauges that need to communicate with a central computing unit, basically. Yes. Right. Any other questions? Okay. All right. So for the cloud brain, this is part two. So okay, we've created the gauges. Okay. We have created the gauge template, but we haven't instantiated them yet. So now we're going to do the same thing with the cloud. Okay. So basically, first of all, we're going to instantiate a bus. So this is going to be basically the bus that we're going to be using from now on. Okay, and then we're going to create a cloud brain. So think of this as the cloud part of the hybrid system, which is going to be the centralized brain that calculates or controls basically how the gauges work and what the system actually does. Okay, so again, we have a constructor, okay, which first is going to take in a bus, right? So why we have created this bus here? Think of the bus as a global object, basically. Any object in our notebook or in the system needs to be able to access this bus. Okay, so we're going to initialize the bus. We're gonna basically so this latest is gonna store the GIDs, basically the gauge IDs, right? Why is this important? Because in a sense, it lets us know where each gauge is as well. So think of this. This is a simple problem. Why? Because we have just a one stream or one basin, basically, which runs horizontally from the headwaters to the town. So in a sense, because of the geometry of the river, we can set these gauges. Basically, their ID also tells us their position and the time the flood is going to reach them. So we can program it way easily by just using IDs. Okay. And then we're going to have some alerts, basically the time when it comes in, which gauge is it coming from, and the stage at which is happening. This is happening on the timeline. Okay. Now the ingest, so basically the cloud is going to subscribe by reading every basin or gauge message on the bus. So the basin or gauge is just our topic, remember? And ingest, what it basically does, it's going to be able to replay these messages up to time t. Okay. So you can basically ask yourself, what did the cloud know by noon, let's say, or by a specific time? Okay. And it keeps two things, which I mentioned basically. The latest, which is going to be the gauge's most recent reading, and alerts, which is going to be basically every alarm it received in the arrival order. Okay. So now comes the real fusion, basically. Now one entity sees the whole basin, okay, which no single gauge can. And let's let that sink in, because each gauge now has a very small amount of intelligence, which for us yesterday was enough to get a clear head start before the flood actually reached the city. But today we can actually have we will actually have a hybrid system that's able to see the whole basin. So in a sense, we can get a state of the whole river, let's say, up like within our gauge system that we couldn't have seen before. And this will allow us to do much more intelligent stuff. Okay. Now this basin board function, so it's basically a snapshot of every gauge's last known stage and whether it was flooding, right? So basically partway through the storm, this shows upstream gauges already flooded, like with flood as the state, and while the town is still okay. So the pattern, this is an important pattern that the cloud will be able to act on, basically. Okay. Now let's run this. So we have both the fleet is ready and now the cloud is ready as well. Any questions? Okay, if there are no questions, we can just summarize what we've done so far. So first of all, we've built the intelligent gauges, and now we've built also the bus, which is gonna take messages from the gauges, and now we've also built the cloud brain. Okay, so we have the three main components that are necessary for building the hybrid system. Okay, the gauges, the buses, and the cloud brain in this case. Okay. All right, so let's go to part three. In part three, we're basically gonna try to assemble everything. Okay, so now a run fleet is gonna be the main simulation driver. Okay, now as I told you previously, bus is a global variable, and here we're actually, when we call it like this, global bus, and we reinitialize it, basically it means we reset the one shared bus that everyone reads. Okay? So every time we run fleet, it's like we remove all of the messages from the bus. Okay? Now, config or basically these gauges. Basically, they're the configs you gave me, or we get them empty. Meaning, are we gonna let the cloud configure the gauges, or are we just gonna use the standard settings? Okay. Now, this is the real part. So far, these are just numbers or names, basically. But what we are gonna be trying to do, okay, is we're gonna be trying to actually implement the network. Okay. So basically, the network is going to give us, in a sense, the geometry of the river or the geometry of this gauge network. So we know which one comes before the other. This can also be done through the GIDs, as we're going to see later. So basically, we're gonna after we have the configs, we have the bus. Now we have the network. Next, we're going to have to actually instantiate the objects for these gauges. So far, we only have logistics. We actually need to bring the intelligence of the gauges to the system. So how we're going to do this? We're going to basically build the fleet here. So we're going to build one smart gauge per each, then step the clock minute by minute, basically. And within each minute step, step every gauge. Okay? Um, basically, this will allow us to run all of these gauges in a sense in parallel, basically. But of course, they're going to interact with the river at different times. Like they're interacting with the river at the same time, but their state is going to be different at different times. Okay. And then we're going to run the fleet basically. So we're going to have the cloud ingest the bus, and we're going to have it list all of the alerts it received. And we're going to see them fire basically from gauge 0, 1, 2, and so on. And this is going to happen around 90 minutes apart. So there's going to be a cascade marching downstream, basically. Okay. We're gonna basically take a snapshot, and we're gonna basically see what did the okay, what did the cloud see up to snapshot, and we're gonna print basically the basin board. Okay, that's right. All right. So as you can see, okay, so the first alert the cloud actually received was on the same day. Remember yesterday we did the storm is going to start on the 16th of July. Okay, we can see the first gauge who actually fired was gauge 0, of course. Okay, then a few hours later, gauge 1 came into play, and it told us what? It told us basically it's rising. Okay. Then a bit later, gauge 0 was already flooded. Then gauge 2 came in and told us it's rising. So see, already by the time gauge 2 came in, we knew at gauge 0 it was rising. At gauge 1 it was rising. Gauge 0 is flooded. Gauge 2 is rising. So see the pattern? It's rising, rising, rising. First one's flooded. Then it tells us the second one's flooded. The third is rising. So you can see basically this movement towards the town from the headwaters. Okay. Now, here we're only showing a few of them, right? There's going to be around 1,690 messages on the bus. And this is how the cloud sees it, basically midday. on the 16th, basically. So we can see at this point in time, the first gauge is already flooded. Okay. The second one is close to being flooded. So remember the flooding threshold here was around 10. And then we can see them actually decreasing as we come close to the town. Um, so see, this is exactly like a cascade. It's basically pointing out exactly to what is happening over here, the first graph that we built. So over here we have the fully hybrid pipeline working as intended. Any questions so far? Okay. Then let's go to part four. Okay. So now, basically, what is the problem? Okay, the moment the cloud, okay, please make clear where are the stage data coming from, showing the codes. It's the same thing we did yesterday as well, basically. So basically, like, okay, let's take a look at this function right here. Okay, so you see these networks, like this is the network we basically build. Okay, so we're gonna basically be taking, remember time was the timeline, okay? The timeline we built at the beginning. So basically this network tells us where are we on this timeline. So similar to yesterday we had stages, right? Today we have this timeline. So here, as you can see, for I in range length of time, we basically iterate through the time on the timeline. So the stages are happening here.
One thing to remember is like, maybe in your projects, right? I mean, you don't want to like, use the simulated data, right? You can either take, IFIS real data or like, USG, yes, real data, right? And then, you can assume that, clouds, edge system is implemented there, right? And maybe you can just like, focus on the cloud intelligence part, right? But if you want to like, implement a communication system, right, from both like cloud and the edge, right, in bidirectional, then maybe you can use this.
Yes. Yes. All right. Any other questions? So now, what is the problem? Okay, so the moment the cloud actually sees Gage's zero alert, it does what no microcontroller can do, basically. We can take this basin topology, or topology basically means like the structure, like geometry or spatial configuration, okay? And which basically is gonna allow us basically to trigger stuff downstream. So by the time the first gauge is flooded, we already know a flood is incoming, basically. Okay. So what we're gonna do is yeah, what we're gonna do basically is we're gonna create a local rise rate. So basically, we're gonna see in this geometry where the rate is rising. So basically, a recent rise rate at a specific reach, basically in feet per hour, is going to allow us to see where this is coming from. Okay, right. So here, basically, it's the location up to basically takes everything up to this point and only keeps the last hour, and it calculates the rise. So basically, this function allows me to see this rise rate anywhere in this river. Okay. Um, uh, this then we have another function called route reach, and basically route reach, what is it going to do basically? So whenever we see this local rise somewhere on this basin, okay, what we're going to try to do is we're going to try to basically project when each reach is going to flood. Basically, when is the gauge zero going to flood, or one or two or three or four, or so on basically. So, depending on the state of the basin, we can have a few cases. So, the first case is basically when we are already flooding, okay? And then we can say that the ETA, the expected time of arrival, is now at that specific point. Then we can have a visibly rising rate, and that happens when the rise is is above zero point 0.3 feet per hour. So basically, then we extrapolate linearly. We see how far it's gonna take from that point up until it reaches the town, basically. And then we can also have a third possibility. It's basically the state is still quiet. So if that is the case, then we can use the basin topology, the like structure of the basin, to calculate how much time it's going to take until it reaches. Okay, so what? Of course, we're going to start with the alerts from the first gauge as a trigger, right? Okay, someone's asking, is it considering the physical characteristics of the basin or simply consider the weather data? Very good question. So here, what is the information we are presented with? We have the basin, which has a very simple geometry. We know the river is coming from this way and it's going this way. Okay, so we already know the geometry. We already know there's specific time depending on the river velocity. So of course you might get this river velocity from weather, like the weather might influence the river velocity and output and whatever. Okay, so you can integrate both the geometry of the actual river, like how it flows, and the other kinds of data like weather data. Yeah, exactly. And based on this, we're going to try to basically estimate. The whole thing we're trying to do is estimate how much time it's going to take from the like from the uh, downstream, basically from the headwaters until it gets to the town. Yeah. Okay, so as I said, we're going to take the gauge's zero first alert as the trigger. Okay, so the instant it lands, basically, we're going to try to forecast all five reaches at once across every core. Okay, and then release them, basically. Okay, and that is called trigger and burst. So it's idle cheaply, okay, but when then there's an event like a flood happening, we react massively on this event and okay, thank you. And we're gonna basically spike the usage. See, so again, the concepts of elasticity are coming back. Okay, so now one basically 60 byte message from a $5 chip spun up the whole machine to a fraction of a second, basically. Okay, any questions so far? But before any questions, let's run it. Okay, so we use gauge zero as the trigger because it was the first one, and we see it triggered extremely early. Extremely early. Like to get a sense of it, it triggered. Where did it trigger? Let's see what time. 7 a.m. on 16. It triggered around here. See? So that's a lot of time before the flood actually reached the town. And let's see the actual numbers. Okay. So we routed everything. Let's see if it actually shows. Yeah, it shows we used a little bit more. I mean, if we all ran it at the same time, it would have used even more. But look at what we can see here. So from gauge zero, we get around 4.3 hours of notice. From gauge one, we get 5. 6.5, 8, and 9.5. So the total time we actually get in advance before the flood actually reaches the town is around 9.5 hours, which is more than enough for evacuation or other logistics. Much better than yesterday. Yesterday we did around 3 hours and we only did it locally. If you remember correctly, we didn't even make it into the cloud. Let me see, I can show you from yesterday. If you guys don't remember, look. So the first time we alerted, the outage was already in. So by that time, we couldn't have sent anything on the cloud. So we were kind of late. But today, we get a head start of almost 10 hours, which is not that bad. It's pretty good, actually. Any questions? Okay, now this is going to be the closing loop. So we have the downstream direction, right? And the cloud has seen gauges 0 alarm, so it knows that there's going to be a wave that's coming for gauges 1 to 4, right? Now, what it's going to do, okay, can you explain what parameter determine the location of time in the code relative to the estimated flood arrival times has been calculated? It was done in the beginning. We did it here. Uh, okay, so we had a storm happening. Remember this is the one from yesterday, right? So we had a storm happening, I think on the 16th, basically. So now we have this offset minutes, basically. And how we're going to basically do it, we have this travel minute time. Oh, sorry, location of the town. Oh, the location of the town is just the location of the fourth gauge. So the fourth gauge is basically where the town is located. Yeah, by design we did this. So gauge 0 is basically in the headwaters, and gauge 4 is basically the town. Yeah. So would you consider this an automated system in computer science? Yes, this is an automated programmed system basically, and it can automatically determine around 9.5 hours early that a flood is coming, which is very useful actually for hydrology applications and even urban planning, safety and logistics. Yeah. Okay. So now this is closing the loop. How can we apply other information about the basin to the hybrid architecture? Well, it depends on how much intelligence you want to give to the actual system. Here, the actual geometry is simple, right? So the river just flows downstream, right? But you can also have different kinds of information. Like, for example, let's say there's another branch coming from a different side. Okay. So if that's the case, all of the gauges that are happening afterwards can have a flood coming from both sides, you see? So we might want to basically have a cut point. And before this cut point, if any of these get alerted, we should probably alert the later ones as well. Can you please explain why hours of notice improved so much? Yes, it improved so much because we detected from around here, basically, around this point, if you see my screen, right? So from around this point, we already saw that it's rising too much. Like it's an anomalous kind of rising. And because of that, by this point, we knew most probably it's either a fluke, right? Or it could be a how's it called? A flood, but it was actually a flood later. So from this time, we're already alerted. You see, so from this time up to here, up to here actually, there's around 9 hours. You see, so that's why it improved so much. Like yesterday, we still knew early, but we only had one of these. You see, we only had one of these. So the best we could do is basically from this alert up to where the flood actually happened. So does this differ from agentic AI? Agentic AI is a like a totally different paradigm basically. It's a system in which we use AI agents basically to perform specific tasks. I mean, you could say this is some form of intelligence, but it's not to the level of like artificial intelligence that we have today. Most of the technologies those use are like more complicated architectures. They're called transformers or LLMs if you're interested. This is just some simple, like we can even do this on like electronic boards, these things. So we shouldn't call it like true artificial intelligence or something. But the idea is similar, basically. We kind of have something like an agent that watches the what the river is doing. Yes. Okay. Can you explain the output of cell 5 again? Yeah. Okay. So gauge 0 alerts at 7 a.m. is the projected arrival time to the gauge 4 and is changing over time. Yes. So basically, at gauge 0, like by the time it reaches gauge 0, the flood, we get 4.3 hours, right? By the time it reaches gauge 1, by the time it floods at gauge 1, we're going to get 5 hours. By the time it floods at gauge 2, 6.5 hours, and so on. So basically, this number is telling us what is the hours of notice that we get from the trigger, basically? This gauge 0 being alerted at 7 a.m. on the 16th, right? What is the amount of hours we get before gauge 4 also gets flooded? So this is what it actually means. Is this like routing, or are you just using gauge information? So in a sense, yeah, it is like routing. It's exactly like routing in a sense, but we are not, think of it like this, full routing, basically, we basically should communicate between these two gauges. Like think of it like this. Routing is usually done. You have some machine which is actually called a router, and you have network devices, okay? And routing, what it does is basically this machine wants to send a message to this machine. What it does, it goes to the router, and the router knows and it sends it to this one basically. But in this sense, we only talk back and forth between the cloud and the gauges. So if you can think of the cloud as a router, but it's not a true router in the sense of like networking. Could you provide a list of places where this kind of tech has been implemented and also project names? So I'm actually not extremely familiar with like hydroscience applications. I think you guys know much more about this, but most probably USGS, NWIS, all of these, they're using probably similar systems, most probably. So similar architectures. Okay. So coming back to this, again, what we have gauge 0 as the alarm. So basically we know that the flood is going to come for 1 through 4. Okay. Now we reach down and we can put these gauges 1 through 4 into storm mode. So instead of having the normal adaptive sampling and all of that, we come back to what we did yesterday. Remember when the storm was on, we would also sample more to get basically a better reading. Because for example, let's say the storm came here at 154, like the or whichever, and you are sampling every 15 minutes. You're gonna know at 2 p.m. that the storm has come. So you lost 6 minutes, which can be crucial in these scenarios. Okay. So basically, why we're doing this is basically to get more granularity so we can know faster. Okay. So we're basically going to have this big function right here run with storm mode. So we're going to have the pass one. So the pass one or the control, basically what it does, it runs the fleet with the default thresholds and records when each gauge naturally alarms. So whenever the rise increases on each of these gauges. Okay. Then we're going to have pass two, which is basically with a cloud in the loop. So the cloud is actually going to perform these things. Okay. So we're basically going to step the fleet again. Okay. We're going to do the stepping, which is basically the running. Um, okay. And okay. But each minute, the cloud basically checks one thing. has the gauge directly upstream of me, which is G minus one. So for example, if it's gauge three, we check gauge two. Has it already alarmed me by now, basically? So, like there are some details here. The inner list comprehension, it basically collects every gauge that has alarmed by time t, and if my upstream neighbor is in, uh, like the upstream neighbor is the one above you, basically. Like for G3, it's G4, basically. If it hasn't alarmed, basically, and I'm not yet alarmed, basically if I'm not, if it's not yet alarmed, the cloud is going to push the mode storm on. So this time we're reaching down from the cloud into the edges, into the edge devices, basically. And yeah, because the storm mode is going to be on and the water rises, you're basically going to cross the threshold a little bit earlier, as I just gave the example. And yeah, we're going to record this new earlier time and see how much it changes from just using the adaptive, like normal sampling. Okay. So basically, we're going to report what for each gauge, how many minutes we gained above the baseline alert time from previous. Of course, gauge zero is not going to gain anything because it's the first one to alert, but every gauge downstream should have some gains basically. And this is the main hybrid payoff basically. It gives us an edge that pun intended that just the edge devices could not have. So let's run it. Okay. So as I said, for gauge zero, we don't gain anything. For gauge one, we gain around the 2 hours, which is amazing. For gauge two, around 2 hours as well, and then 1 hour and 42 minutes. So not bad, basically. And also let's see a plot. Okay. See? So we were able, like, first thing, what did we do previously? Previously, we just alerted the system early that it's happening. Now we're gonna alert the next gauge, basically, to start a 1 minute sampling instead of 15-minute sampling before it actually gets alarmed. So, but this only works because of the basin geometry, which is an important hydrological fact. Okay, so we actually did even better than just alarming early. And 2 hours almost is very good. Is very good as an add-on, basically. So think of it as instead of 9.5, it should be around 10 hours, basically. Any questions? Yeah, we gotta wrap up. If there are no questions, we can quickly run part six, which is just going to show us the scoreboard, basically the different designs and which one's the best. So on Tuesday we did cloud only, and the town lead time was just 3.5, basically. Okay. Yesterday we did edge only, basically, and we had a local siren that was running again 3.5. Today, we did a hybrid system and we had around 4.5 average lead time. So as you can see, the hybrid architecture outperforms both individual architectures. And this concludes our workshop. So if you have any questions, please let me know.
Okay, right. Thanks, Mihail. So I think this afternoon we're meeting again with the fellows, right, in a bit.
Yes.
But for all the participants, thank you very much. So Vidya, I'm not sure if like everybody's going to attend tomorrow's session on Alra Center, or is it only for the fellows?
Yeah, no, it is only for the flows. Um, thank you everyone for your participation and engagement in our program. We appreciate your participation. Let me share with you our YouTube channel again in case um, you guys want to go through the videos, the training videos. So these all are, or I think, can you make me co-host? Bijaya, because I can't post any things since I.
Yep, you should be able to do it now.
Great. So this is our YouTube channel again. If you miss any training, so all videos are available. We will make this today videos available this afternoon. So you can go through the videos and then learn. If you have any questions, you can always reach out to WaterSoftHack@clemson.edu with any questions or concern you have about the program, about hand-on training, coding, or any materials that you need to learn. So again, please respond to our post-event survey and let us know what works and what didn't work for you and what would be your suggestion for us to improve our program and better serve our community. Thank you to Mihail and Bijaya for wonderful hand-on training this week. And then we will continue our program with our flows. Tomorrow we will have science communication with our flows, and then next week will be a capstone project presentation. I will send a Zoom link to you, all of you, to attend the flows presentations on Friday 31st, July 31st. So look for an email from WaterSoftHack team regarding the flow presentations. And once again, thank you for your participations, and we wish you well in your career and the work. Thank you.